I have never seen on the exam a place where you have to use this method. So the methods that we've done so far for figuring out volumes by revolution, just using the circles or the discs, pi r squared, on every exam, you can always do that. Okay? This is really cool, in my opinion, but I like math stuff. It's a really cool application, but if you don't know it on the exam, you can still use the other methods. But sometimes this method is way easier than the circles and the discs. And I'll show you what it looks like, okay? So what this method, the cylindrical shell method, is basically you've got a cylinder, like a shell of a cylinder, like a tin can that's really thin. And we make the thinness of the tin can really small. So small so it's almost like paper. And if we added up all of those paper-thin cylinders, we would eventually get a volume. So here I have got this paper-thin cylinder. I cut it and lay it out flat, so it's like a piece of paper now. And that piece of paper has circumference as its length, because it went all the way around the circle. The function as its height, and a depth of dx, super tiny small. Okay? Then if I want to add up a bunch of cylinders to get the volume of a shape, it's just going to be the formula for the volume of the cylinder, which is 2 pi x times f of x times its thickness, adding up all of those along the way. So the volume of one shell is given there, and then the volume of the whole shape would be all of the matter. Oh, I want to go back to here. No, that's good. So visual tips on drawing a cylinder. Take any point on the curve, draw the radius perpendicular to the axis of rotation. Drop the height from a point parallel, and then we're going to drop. So we'll look at this with some examples. And notice that you can take out the 2 pi part out in front. So here's the idea. If I was taking this shape and rotating it about the y-axis, option 1 would be to do the circle method about y, right? In which case I'd have to rearrange this formula to get x equals in terms of y, which is a little bit complicated. This is why this is a great example of one they'll never ask you, because they'll always ask you one that would be easier. Okay? And then you would rotate, and then the problem with this shape is if I rotated it, I'd sort of have to do, cut it in half and sort of do it in 2 different shapes, because the y's, there's going to be one volume up to here and a different kind of volume after that. So sometimes our circles and our discs methods get complicated because you have to break the shape up into more than one thing. Not hard, just annoying a little bit and tedious. Okay, so we're imagining this thing rotated 360 degrees around the y-axis. If you pick a single point on your graph, this would be the height, and if it got rotated around, that's the shape you would get. And if I think of that as one tiny cylinder, then I have a cylinder. And what the cylinder method lets us do is it lets us move the cylinder along the x-axis and keep it y equals 3x minus x squared. And we don't have to worry about 2 different parts because the height changes nicely as we go along. And it would end up looking like this. The circumference of our cylinder will be 2 pi r, and the radius is whatever x is, so we get 2 pi x. The height of our cylinder is the function, that's the 3x minus x squared. And the depth of our cylinder is dx super tiny small. If we integrate this from 0 to 3, that would add up all of those cylinders as we go along. and we would get an answer for the volume. This would be an example that using the circles method would be complicated because it would be hard to get x in terms of y. You'd have to use completing the square or basically quadratic formula to do it. Not very much fun. So with that in mind, we're going to skip the next two examples and go to page 26. For those of you that don't like things skipped in your notes, you'll have to pause the video on these, because I'll show the answers shortly right now. You could hit pause right here and pause right there and try it on your own if you wanted to. But we're going to save time and just do another example where the drawing is already there. This is on the bottom of 26. And this is you could do the cylinder method over the x-axis too. But notice that the cylinder method, when we went over the y-axis, which would normally, with the disk method, mean that you did a dy, now you're still using the dx. And if you revolve about the x-axis with the cylinder method, now your cylinder is going around y, not around x, which we can see in this next picture. Okay? So now here's one cylinder. Here would be another cylinder. Right? And as the point moves along here, your cylinders would all get added together, and adding all of those cylinders up would end up giving you the volume as if it was revolved around the x-axis. But your cylinder is moving from this y value to this y value. So our cylinders are rotating or are in different forms. Again, this would be very hard to do with the disk method, because if you wanted to use the disk method, then you would have to go from here to here. And you would have to figure out where that point is. It's not given to us. You would also have to do at this section and this section separately, because they're like different parts. Part of it's like subtracted and part of it's not. So it gets complicated. Okay, but we could easily figure out these two y-intercepts by plugging in 0 for x and solving for y. Factors nicely. 2 pi r. So now the length of your cylinder when it's opened up is the circumference. That's your 2 pi r. The height of your cylinder is your function, which is given to us. And the thickness of our cylinder would be dy. Adding up all those cylinders, again, now it's just the math part, lets us figure out the volume that we couldn't figure out otherwise. So again, we're going to skip the next question. I'll put it up so you can look at it and imagine it if you want to. And then we'll just go to the bottom of page 27. Everybody done good here? Almost? So again, I will show the numbers here. If you want to pause this later and try it yourself, you could. This one's really cool because it's using the cylinder for this part that's in between these two, if that was rotated around. And it makes it a lot easier than doing, if you wanted to use the disc method or, yeah, we'd have to use the washer method here. It wouldn't be as easy. But what I show at the bottom is that if you had this region R and you were rotating it over the x-axis, you see that your radiuses would naturally change and the disc method would make the most sense. But as soon as I wanted to take this region R and rotate it over the y-axis, the disc method actually would work fine until here. And then we got problems. Because now this little part gets, but not here, but then this, like, oh, now my discs don't seem to work or my washers aren't, it's just complicated. So if your radiuses, like you see how my radiuses stay nice and easy along here? That makes the disc method easy if I'm rotating across there. But my radiuses this way, they start off fine, this would be no problem until, oh my goodness, now I have that little part and this part and this part, and then how do I, it's just not nice to do it that way. So if your radiuses can stay nice, this would be one where if you were doing it about the y-axis, it would make sense to use cylinders to go about it. Okay? So my guess is, they'll give you this question on the exam, they'll just go over the x-axis. They wouldn't dare try to do it over the y, because it would just be not nice. Okay? If they're going to give you one that's not nice, either over the x or over the y, it'll be not too bad to do with the washer method, that you'd probably still choose that. However, if you chose the shell method, because you're like, oh, this is cool, and you spend the time and learn it and like it, and you use it on the exam, you'll get full marks for that. Okay? So here, if I was rotating this one over the x, from here to here, it would just be this minus this. You'd have nice washers. But can you see, at this part here to here, it starts getting messy. Like actually it's okay for a washer up to about here, right? Because you get big radius minus little radius. But now you'd have to do this little tiny section differently. You'd have to find out, this would be my upper function, that's my lower function. You have to break them up into different equations. It was almost impossible. So here, using the big radius along your y would mean that if you went over the x-axis, you would definitely use the shell method as like the only way to do it that would work out nicely. So just seeing where this is useful. Okay. So we're gonna do the washer method, because that's good review for us. And then I'll show the answer again. If you want to watch it on video for the shell method later, you can. But what we've got here is two equations. Y equals the natural log of x, and y equals x minus 2. And we want to revolve it about the y-axis. So if I want to use the disk method, my big radius would be the straight line. My little radius would be the ln x graph. And if I want to use the washer method here, I have to rearrange my equations so that they're in terms of y. So these ones aren't bad to do. It's not hard to get x by itself with this one. Just move the 2 over. This one's a little bit harder. You have to change it to exponential form. But you're going to get e to the y equals x, just by using the definition. So our washer method, have to take out our calculator. Lovely intersection points. Now, which are the important intersection points if we're using the washer method? We're really concerned about the y values. So we have this negative 1.84 up to this y value of 1.146. 3 decimals. Those would be the values that we're interested in. And so now we're going to integrate, right? The washer method, the disk method, uses areas of circles. So we always have pi r squared. I can be factored out because it's a constant. But notice we have the big R, right? There's my big R, that's my line. That's going to be y plus 2 squared. Minus my little radius, that's going to be my e to the y squared. And we're assuming this is a calculator question. If it's a calculator question, don't actually integrate. Don't waste your time on the exam. If you have your calculator, just type that in and push enter. Even if you're not impressing anyone on the exam, they're not going to be like, ooh, I'm so proud of them, they can integrate e to the 2y and get e to the 2y divided by 2. Good job. No. They're like, I'm actually less impressed that you didn't realize you should just use your calculator and get the answer right away. Okay, so on the exam, if you're on the calculator part, be careful you don't get drawn into non-calculator rabbit holes where you do a bunch of algebra you do not need to do. So I could just type this into my calculator and get the answer. And this would be, right, if I wanted to figure out, like this part here, would get rotated. Right, there's my disk. Rotated around, and I'm adding up all of those disks from negative 1.84 up to the 1.146. This same question could be done. Oh, I didn't mean to erase all of them. Okay. I'm not hitting the undo button in the right order. We'll just imagine you can't see that number anymore. I will just rewrite it in 1.14619. Perfect. Yes.
I don't know if you're muted or not, but you have like a mute icon.
This thing? This is going. This button, I think that's muting sounds out of my computer.
Oh, okay.
I'm full. Okay. So now, if we were doing the same thing with the cylinder method, now this becomes the height of my cylinder. that would get rotated around. And if I added up all those cylinders, it would give the same shape as all of those discs. What's the nice thing about the cylinder method in this situation? My cylinders would start here, and now we would need my x coordinate of 0.1585, all the way up to my x coordinates here, which is at 3.14. 3.1416. And I wouldn't have to, I'll show this one, right? There's my cylinder. My radius is going to be my value, my height is the distance in between. Same intersections, but now my integral goes from the x value to pi r, and my radius is whatever my x value is, so it's just 2 pi x. And my height is the top function minus the bottom function. So I get ln x minus the x minus 2, which I distributed it to make negative x plus 2. You know what? I visually, I like an extra set of brackets. You okay with that? It's really more visual then. We have our top function minus our bottom function is our height. We get exactly the same answer, typing it into our calculator. So this could be an exam question, because it wasn't hard to rearrange the equations to be in terms of what? It wasn't hard to use the disk method. We had to use our calculator to find the intersection. Is the shell method a tiny bit more efficient? Yes, because we didn't need to switch the equations, but a little bit more thinking. So what you sort of have to do if you're imagining these is you have to imagine, do cylinders stay nicely as I drag it from one value to the other value? And if you think about a bunch of tiny cylinders and drawing them all, would they fill it all up and make the shape? I found some really nice videos of graphics of showing the cylinders added to each other so you can see the whole volume. But I don't know where they are right now, so I'm not going to show them to you because, but if you just like search up shell method video, you'll see someone who's created an app that does it nicely. And it's just a nice visual because it's kind of, it's probably pretty good for your brain to try to imagine. Can you imagine the first cylinder? And then the second cylinder? And then the third cylinder? And then the fourth cylinder? And so on. And then as you keep putting them together, can you see the volume of the shape filling in as they're all put together? Not that easy. Not that easy to do. Maybe I will start. Now I want to start searching. Okay, I'm going to stop that video there.